Okay, we've got a chain. I put this chain on a balance. Accurate 2 grams. And came out 358 grams or something like that. I rounded that off to 400 grams just to get the ballpark idea. And I just stretched the thing out between my arms a couple of times. My arms span almost exactly 16. So came up with pretty close to 5 meters. Okay, those things could be modified, and probably actually will, maybe even will measure this. And the tension is 4 newtons. You just assume a tension of 4 newtons. Okay? We can achieve that very easily. And just put one end at something like hook on the wall, and we hook 800 grams over a pulley with low friction. And we get that much in. And then we could actually observe the frequency of the second harmonic. So how do we predict frequency of the second harmonic? I said you can do a couple of things. You can say, well, what do I need in order to get the frequency? What kind of things could I combine to get the frequency? You could sit and make a list of things that I could combine, maybe 2 things, maybe even 3 things that I could combine to get the frequency. Okay. And then you ask yourself, how do I do this? How am I going to get this? Or how am I going to get this? Another way to approach it, that's kind of top down. It's a good way to approach things. Bottom up isn't bad either. Bottom up, you can take what you've got and determine whatever it is you can determine from that information, and then see if you've made progress, if any of that helps. Find the frequency. Okay, so I gave people a couple minutes, just took a walk to Holland back, and came back and said, one person said, well, I've got the wavelength. Another person said, well, I've got the propagation speed. Okay. Make sure it's a propagation speed. It's clear, whatever words we use, because that's what it was. Okay, so that's good. What's the wavelength? Wavelength is a length which is a thing which is 5 meters, because of course the second harmonic has this configuration with a full wave. Yep, every configuration. Okay, and in this case, wavelength is equal to the length of the. Okay. So that's good, and then speed. And let's come over here, so I'm not blocking the board as much. Square root of h over mu. Book uses mu. I like it too. And that's going to be easy. Mu is the mass over the length, which is 80 grams per meter, or 0.08 kilograms per meter. 0.08 goes into 450 times. So we get, I think, about 7 meters per second. You can check that. You can do the whole thing symbolically. We just use lambda equals L, C, square root of T over mu. Yeah, but these are the approximate values of those. We could use those. We're going to stick kind of with the symbols. But then, what do we get for the frequency? Well, there's a formula. You multiply the wavelength by the frequency, and you get the speed, propagation speed. So very quickly get frequency is propagation speed divided by the wavelength. So if you're going to do symbols, you get that. Okay, but I like also asking the question. If the thing is 7 meters long, moving at that's our 5 meters long, moving at 7 meters per second. Then it's going to take a little less than a second to complete a cycle. Now, if this wave is moving at a little more than 7 meters per second, every time it moves a wavelength, we go through a complete cycle from this to this and back to this. Okay, from this configuration to this configuration to this configuration. And that's going to take 5/7 of a second, which is about 0.7 seconds. Okay. Oops, but okay, that's the time it takes. The frequency of that's the reciprocal, the time it takes, it'd be about 1.4 seconds. It would be 1.4 seconds if these numbers are absolutely correct, but this is a round off. I'm getting like 0.707 or something like that. If the numbers in my head are correct and I'm not checking it. Okay, so don't lie. So get this, okay? So yeah, but if we use this with this and this, put all of them together. What's the frequency? Well, it's a square root of T over mu divided by L, which is the square root of T over mu L squared. And then check if the numbers work for that. These are all in SI units. So we just do the numbers. We know we're going to come out with units of what? Tension is force. We've got a mass per unit length here. Mass goes into the force, giving us units of meters. And then we have mass per meter, mass per unit of length. I'm getting a unitless quantity here, but that can't be right. Well, let's see if the numbers come up. I think I should get reciprocal seconds. Oh yeah, I still got the reciprocal seconds squared from this, from the tension. And we get reciprocal seconds, so the units come up. Okay, you want to check that. Every time you're doing an analysis of something, every few steps, do a dimensional analysis. It catches a lot of errors and prevents you from going on and building on errors and wasting a lot of time. It takes a little time to do the dimensional analysis, but you got to always check if what you're doing makes sense. It's one of the things I'm going to have you do. I worked it out. And I caught a couple of errors just by doing dimensional analysis. It saved me some time. It's fairly complicated. Okay, this is real simple. Now, if we put in 4 here, and we put in mass over length, which is numerically 0.4 over 5, okay? And that's 0.08. That's for the mass per unit length. And 5 for L, what have I got? I've got 4 over 0.08 times 25. 8 times 25 is 200. So that would be 5 over 2, which is I don't know, I'm losing track. Okay. Anyhow, you can check that and see if it works. But if this and this agree, then you know you have good agreement, and it's a good way to convince yourself that you got it right. It doesn't then make sense in terms of intuition. We've done the thing with the rubber bands, we're pulling back, wiggling them, okay? Haven't analyzed those yet. We've got a feel for that. We know how to get the second harmonic. If I did it with this heavier chain, which is about 15 times as massive, but of kind of similar length to the rubber bands, would it make sense that if we wiggle back and forth at about this pace, 7/10 of a second between cycles, 1.4 cycles per second, that we might get the second harmonic? Well, It's gonna take about 10 hours to figure it out, so let's get it. See what it takes to get the second harmonic. We're not gonna measure the force, we're just gonna estimate it. Okay, now, get a little trouble getting it going. Everybody eventually managed, a lot of times kind of a circular way, that was okay too. And that's kind of instructive, to get into polarization. Okay. So I think when people got it going, they got one at about half a second. Okay, pretty close to half a second, maybe even 4/10. Period. So the frequency is more like 2.5 cycles per second. The frequency is like 2.5 cycles per second. You could work out what the tension would have had to be, right? Matter of fact, you got the formula there if you can derive it. I don't advocate memorizing things like this since they can be so easily derived by putting together fundamental facts. Okay, but right here we've put fundamental facts together into a formula, so we can change the frequency, keeping this and this the same, and solve for t, right? So the frequency is 2 NSI units. Mass per unit length times L squared is about 2. So that's about 4. The tension should be square root of 4, should be about 2. Something. Yeah, but we can make that adjustment. Okay. If F is not given T, U, and L, simple variation problem. How would you answer that question? By what factor would the frequency change? Okay, I wrote 0.7 seconds down here. I changed the number to 1.4. That should work. And I just said, okay, let's just put subscripts in this. F equals F naught. And it's no forgive T naught, mu naught, L naught, and so forth. What is that if T increases by 15%, L decreases by 20%, T doubles, T doubles. Okay, this is what we would do with the chain that we use. If we grab the chain so that the length that's oscillating be 20% less. So instead of 5 meters, that'd be 4 meters. And we put 4 meters into the equation, that would be ridiculous because we can do it with one calculation, as you'll see. So the chain becomes 20% less. We haven't changed. We haven't talked about the mass per unit length. Okay. And since this thing is in terms of mu, I'll say that mu is unchanged. Everybody read cursive? You're culturally illiterate if you can't read cursive. That's assumption. Okay. I'd be taught to write it. It's ridiculous. There's a lot of brain development that goes on with linear multiplication. Nearly broke my brain, doing terrible. It probably gives. Okay, anyhow. So again, we're gonna grab the chain a little closer, so we've only got 4 meters of chain. We're gonna increase the tension 15%. Okay, so we just use weights hung over pulling to get the right tension. We just add a little more weight. And that's that T doubles. See the problem because I said T here, T here. Here's still unchanged. Didn't mention you. You could have said, okay, well, the mass stays the same. You could have done it that way also. So again, we just got a tension increase of 15%, a length decrease of 20%, everything else is the same. So what factor is the frequency going to change? Give me just a minute to think about it. F is proportional to the square root of T. If only T changes. It's proportional to the reciprocal of L if only L changes. So it's proportional to the reciprocal of the square root of T over L. So F changes by factor. Careless. Over 1.15 or 0.8. Or 1.15 is about 1.07. 1.07 divided by 0.8 is about 0.1375. 1.07. It's about 1.34. We got frequency 1.34. Now that's intuitive, but you should have intuition about variation because it's very, very helpful in engineering and in physics and lots of other places. I'll say review, but maybe you never saw it. Will be much to your benefit over the next 2 years and beyond if you get the idea of proportional variation down now and start using it when you reason out certain situations. Okay, now you get you a little bit, you can find all kinds of resources. Find one that makes sense to you. Find one that's the right level for you. Things like review proportion variation for nuclear physicists. You probably get something pretty interesting, actually. Ask ChatGPT to explain it to you. Okay, or Bing, whatever. Get something that makes sense and is consistent with ideas as well. You know, okay. You could write F naught is a square root of T naught over U naught L naught squared. Right there it is. We can plug these numbers in, but the numbers all factor out and the other stuff stays the same. The other stuff just gives you F naught. So right there's a factor by which frequency changes due to these changes in length and tension. Okay. So that's very straightforward. There's just nothing much more than algebra 1 in that. Okay. And it doesn't get taught because people with average ability have trouble understanding it. So people with high ability never get to see it. It's really, really, really stupid. And then they get into engineering and physics in their second year of engineering and they're doing great. They've got advanced mathematical skills and everything else. They can't think this way. Fortunately, it's easy to learn to think this way if you have kind of aptitude we have in this class. But you can teach people the mechanics of doing this. I did it last semester pre-calculus. I'll do it again this semester in pre-calculus if people start coming to class and doing their homework. And we'll get it in 30 minutes or less. And then they don't practice it and forget it, but they get it. If they follow up, then they have it. And it's handy, not just in engineering and physics. Okay. I don't know how much of that I recorded. Like all I was saying was, at first I just, wrote down that F naught is what you get for T naught and U naught and L naught. So then if F equals T over mu L squared, and T is 15% more than T naught, and L is 80% of L naught, 20% less, you get this, all the numbers come out here, you get 1.34, and what's left under here when you take the numbers out is the original. I say review portion of variation. It'd be very good. I went on some length, and it might have been, I don't remember that. Okay, you put the motion for second harmonic. That equals this, speed propagation equals this. This is something you should know from the introductory problem sets. You should be able to easily write this down. has this form. It'll tell you what the average is. Here's the amplitude, and you know what I mean by that. And this is the graph of y equals sine of kx for the second harmonic. I wrote a bunch of stuff here. This is a graph of this function if the cosine equals 1. Okay. Now, what's the graph if the cosine equals -1? You remember that picture? Probably the curve that you would have, cosine equals -1. Okay, so what's the graph look like if the cosine of omega t plus pi equals 0? Simple gesture to show me. It's not what the graph would look like. It's not. Yeah. First thing I was, yeah, all the y's are 0. That's not the graph. I knew that. Before. We'll see. And in between, if the cosine of omega t plus pi equals 1/2, then you'd have a curve that is twice as close to the flat line. Okay. And it goes from one to the other because, well, as t changes, at some point the cosine is going to be 1. A little bit later, cosine is going to be 0. That's going to go to -1. It's going to go to 0. And it's going to go back to 1. So you're going from one shape to the next, back and to the original shape. Okay. So that gives you, I mean, that's what you were looking at. You see how that's what you were doing? I mean, that's what the wave looks like. Okay. And that's how it moved through its cycles. Now there are more details, like what's K. How do you reason out K? Okay, and I got something I didn't understand all the words, but I think it's going to be correct. That involved the formula 2 pi over something. Okay. If the length there is L, then it's the value of K. there's reasoning. Not just formulas you're gonna forget. We're getting mixed up on. Is there a bunch of formulas where 2 pi pairs and 4 pi squares and, you know, similar expressions all over the place. You'll never keep it straight. Unless you have just really a great memory. I mean, some people can. I couldn't. I just learned what they meant. Or memorize them short term, but I didn't like that. Yeah, when you're in a pinch and you've got an exam coming up in an hour, you better remember. If you don't know how to reason. These were in higher level course, senior level. Atomic and nuclear physics. It gets really confusing. So confusing that our instructor is teaching us out of notes that he developed into a best-selling book on the subject. Let us use a 1 inch square cheat sheet that we wrote by hand, so we keep the formula straight. I found that by the time I made that cheat sheet, I really didn't need it. I had it with me, but I never even had to look at it. I kind of always advise this for that. Make the smallest cheat sheet you think you can get by with. And by the time you've reasoned it out, you probably don't need it. Okay, well, all that's relevant. Well, there's the equation of the wave. Now, what about this cosine of omega t plus phi? If you want the wave to start up here, you can just let phi equal 0. If you want the wave to be this one, when t equals 0, and just let phi equal 0, you just got cosine of omega t. And when t equals 0, it's 1. Okay. If you want the wave to start with a flat line going down, you want cosine to be 0 going toward negative. Okay. Well, that means phi is going to be pi over 2. You want to start down here, you let phi. You want to start here going up, you let phi equal 3 pi over 2. Hopefully you encountered some of that in differential equations, but not necessarily. It depends on how the instructor chose to prioritize different aspects of the course. Okay. I'm sure I got all this. So give me an equation for this chain. Okay, you've got different situations. You've got a plane wave. Here are the peaks of your plane wave. Here's your wave. Assume propagation speed c1. Here's your direction of propagation. Here are your peaks. This is the transverse. Transverse remain the peaks. Basically, the line with the peaks runs perpendicular to the direction of propagation. We have an interface here. Maybe this is piece of glass. Okay. So this propagation speed decreases to C2, which is less than C1. Okay. Index of refraction is N1. Which is C1 over the speed of light. And I've got that upside down. And also, get the equation over that. N2 C light over C2. Now you can work it out. If you take what happens, let's say, when this line of peaks, it's this point. And again, by plane wave, I mean the peaks are all in a plane perpendicular to the direction of the propagation. So this one hits here, but the rest of the wave, or some of the rest of the wave, continues on until finally the next peak is entirely inside of the blast, let's say. Okay. Then you could think of this part of the plane up here for this distance is less than the original lambda. Okay, so let's call this lambda 1. That's the wavelength in this region. Okay. So this peak also comes up. Well, after just remember to draw this whole thing. Don't worry about it. Okay. At this point, the peak here, there's a peak here. Okay. And now the peaks are in a plane. That's very misleading. Gotta fix that. Hang on. Okay, clearly, this peak occurs later than this peak, right? So all these peaks occur at the same time. All the peaks on this thing occur at the same time. What's going to happen is this one is going to move forward a shorter distance because light has slowed down. Okay. Now the peaks are here. And the wave is now propagating in this direction. Okay. Now simple trigonometry tells you, of course, there's a new direction of propagation. So let's say we should take this arrow that it's the interface here, and then this arrow here. It's parallel in the new direction of propagation. Because same thing's going to happen to all the peaks, all the way up the interface, right? They're all going to slow down when they get there, but these get there later and causes peaks to line up in a plane that's not parallel to the original. Okay. Now you look out the trigonometry of this, which is simple, but I don't take the time to work through. Okay. Here's your new direction of propagation. It's not perpendicular to the surface. Here's the normal to the surface. This line here is normal to the interface. And the angle that we have here Kind of small, theta I or theta incident. This is the direction of the incident beam. This is theta sub r, which is the direction of the refracted beam. Now, you made note of Snell's law when you went through the introductory problem sets and the pictures. You know Snell's law? Centers. The sine of theta r divided by the sine of theta I. And you see that sines and cosines and stuff naturally come out of the triangles that emerge in this picture if you try to analyze it. Okay. If you know how much this thing slows down, then you know the slope of this thing. And from the slope of this thing, you figure out theta r because it's perpendicular to it. It's going to work out that sine theta r or sine theta I equals what? It's going to be a simple ratio. Is it n1 over n2 or n2 over n1? You read that out? Okay, well, you can memorize it, so this is n2 over n1, and that's right. But reasoning it out, it wouldn't make any sense to have n1 over n2. Why? This angle's smaller than this. You know, you're turning closer to the normal, and if you don't see that from the picture, draw it out and think it through yourself. Or find an explanation somewhere, but it's pretty straightforward. Okay, sine of theta r over sine of theta I, then it has to be less than 1. Okay, now which is greater, n1 or n2? Well, C1 is greater than C2. So it looks like the reciprocal of C1 will be less than the reciprocal of C2, so that N2 is bigger than N1. Okay. So it's N1 over N2. N1 goes with the incident side. N2 goes with the refracted side. And if it's, as I'm saying, if this picture makes any sense, you can see which way it has to be. And you can work out the trigonometry. Okay. It's pretty simple. Now, there are more sophisticated ways to do it. There's a Huygens principle and stuff like that. Okay. That's a more rigorous way. We're doing a fairly quick run through of this, but we want to take it to some level of depth. So now that we know this, it's not really. And you can also work it out with the equation of the crowd. That's something that's accessible to somebody with good trigonometry skill. Analytics trigonometry. We also have good analytic trigonometry. I don't mean down the road good, but really solid. Well, very good source. Okay. Not great. Okay, now this represents that vat of water to around the laser beam. Okay. So we run a laser beam through the center. And there's your central. Then we run it through another way. Right? This distance is y, and it's quite a bit less than r, so that like the sine of anything is equal to theta. It refracts at this point through the only thing you can see, which is this tangent. Now, perpendicular to the tangent plane, the radial line, which is normal, the tangent plane. So now we know the angle of incidence, don't we? Right, there's your angle of incidence. So you're going to have an angle of refraction. You're going to refract to a smaller angle because this is water. Water and glass have not exactly the same index of refraction, but it's close. If you look on an index of refraction table in your book and Google it even faster, you get close. Write down something common, like water and glass. And different kinds of glass will have different coefficients of expansion. Somebody asked about oil, you can look that up too. Okay, it's coefficient or the index of refraction of oil. That tells you the factor by which light slows down, where it enters water, where it enters oil, where it enters another glass. Okay, so now we've got this relative. Let's make this bright red. It's going to refract closer to the normal. Now it turns out if this is a cylindrical diamond, that it'll refract so much because diamond has a coefficient an index of refraction of about 2.5. If I remember correctly, you can look that up, verify it. But that's kind of an easy number to remember. At that index of refraction, this thing will actually cross the line of the central group. Okay. So it'll hit the other face on the opposite side of the central group. There's nothing we can bring into lab. It has that kind of coefficient of refraction. So we can't even observe that. And the coefficients for water and oil and that other thing glass are generally around 1.3, 1.4, maybe up to 1.5% of glass, something like 2.5. So for stuff we can actually observe. This thing is going to refract. I'll call theta sub R1. Now, theta sub R1 there's a tangent plane here, right? So we're going to have again normal line, which is radial. Well measured point so it's normal to the tangent plane. So we're going to have some angle I'll call theta sub I2. Because now we regard the beam as being incident on the opposite face. Okay? So it's going to refract at some angle, and the angle is actually going to be bigger than theta I2 because we've gone from a slower to a faster medium. You want to digest that and think about why it's so, but it's so. So this thing is going to refract back closer to the central beam. And we call this our focal point for this thick lens. Okay. Now you can work that out. Work it out for index of refraction 1.4. Work out these angles and these distances. Now, if y is much less than r, then the distance from here to here is pretty much just the diameter. It's a little less than the diameter, but you don't have to worry about that. Okay? If you worry about that, as you do if it's way out here, if it's incident way out here. But if you stick with y much less than r, you'll find that the focal point, position of the focal point, doesn't depend on y. Small y and on y. This means that all the rays that hit here probably about this much of the sun are going to focus very near the center point. And we can see this. All we have to do is take that cylindrical container full of water, okay, and mask off all but, say, an inch in the center. Put a light source there, even if it's a faint one like a candle at a distance of 6 feet. Look, it's a pretty bright image on a piece of paper. It'll shine right through the paper. You saw that, you'll be able to see that, and you'll see that it really collects the light. Okay. Now that's a pretty good exercise in ray optics. You also want to read how images form with thin lenses. Okay, this is a thick lens. With a thin lens, it's like we shave off a little bit of this thing. So we shave off this much of it. So now we've got this thing here. We bring that down here and set it up. This is a thin lens. It's a thin cylindrical lens. Difference between the thin lens and this one is that when a ray comes in here, it gets refracted and then refracted back. It doesn't go very far within the lens, so that the line of the refracted beam very nearly intersects this point where the beam is incident on the lens. So that this ray, and that's, it's not going to be that much, gets refracted down this way, then back this way. It's not going to be as much. But the two rays almost intersect at this point. The thinner the lens, the closer they intersect. So you can treat it as if the thin lens simply bends the thing in a continuous line with one slope here and one slope here. Okay. Unlike this, where you've got the whole lens to pass through and you significantly change. So that this thing, this refracted ray here is not going to come very close to this incident point. Okay, the line of the final refracted ray is going to be pretty far from the point of intersection. Maybe not as far as I indicated here, but it's going to have a significant difference. And all that is important and worth digesting.